Okay, let me begin. So the idea of this lecture is to introduce you to visualization techniques that focus on a different type of data, so namely vector valued data. So far, we have looked at scalar valued data. The techniques for vector value data or vector fields, as they are called, are slightly different, as we will see, right? So to begin with, what do we mean by a vector valued function, right? Um, a vector valued function is one where at every point um, on the domain, you have, for example, if the domain is two-dimensional, then at every point on the domain, you have a vector, right, mapped from that point. So this is, in this case, R2 to R2, right? And this range space can be considered as a vector which has some magnitude and a direction, or it can be considered as a point again in 2D. That's just up to our interpretation. A very simple way to visualize this vector field is to simply just draw these vectors in place, as you can see here, right? In the figure here, what you see is a collection of let's see, let me switch. Right. What you see here is essentially a collection of vectors displayed as glyphs. These are called glyphs. So in this case, the glyph is an arrow, which indicates both the direction and the magnitude of these vectors. This is probably the most simple and obvious form of visualization. Sometimes these are also called hedgehogs when you don't show the arrows. Of course, you can incorporate color to indicate a few additional properties. For example, here color, I think, refers to the, if I understand right, so it's the direction. So X, Y, and Z are mapped to different colors, and the color tells you in what direction the arrows are pointed. The color could also be used to indicate magnitude. So these are obvious visualizations, not much to think about here, but of course there are limitations. For example, if as the data becomes large, you really are not able to make much sense out of this visualization. Early on in the study of vector field visualization, streamlines have been proposed. So a streamline is essentially capturing the essence of the vector field in the following way. So streamline is a collection of curves. Each curve here, for example, is essentially obtained by looking at the vector field at a particular point and integrating along that vector and so on, right? So the streamline is essentially an integral line that is defined by the vectors. So you can think of this as a maximal curve as in you keep extending the curve as much as possible. And at every point on this curve, what you have is that the tangent to the curve is equal to the vector at that particular point, right? So that is how the curve is defined. So I'll state that again. So you take any curve here, so any maximal curve as in you go till the curve cannot be extended anymore. So it's a maximal curve. At every point on the curve, what the property that you have is that the tangent to the curve at that point is equal to the vector at that particular point. So you can quickly see that when the vector goes to 0, this is what will happen when you have something like a sink, right? A sink point where all the vectors go plunge towards it, right? So you may have like a sink here somewhere here where the vector goes to 0. So there is no streamline associated with it. In the neighborhood of a sink, you will have vectors that point towards it. Similarly, you have source points and so on. So streamlines are able to capture the overall behavior of your vector field quite well, and hence they are quite extensively used in practice, right? Now, of course, the question is how many streamlines do you want to show? Now, the streamlines, as you can imagine, will cover the entire domain. So there are infinitely many streamlines. So you have to sample them. So here is a sample on the right, which shows a sparse collection of streamlines. This is quite useful to have a sparse collection, but how do you compute this sparse collection? This is a research challenge. Sometimes you want equally spaced streamlines. So here is a visualization of the same data with equally spaced streamlines. This is often useful when you want to understand the overall behavior. In other cases, you may not want equally spaced. You may want streamlines that focus on the features of interest. For example, you highlight the source, and so here is a spiral sink or a source, right? And you may want to highlight such behavior. So what you do is you your starting points for the streamlines will be seeded here near the source or the sink, and you extract streamlines from there, right? And hence get the visualization such as this. So you can already see there are many possibilities. There is no one approach or no one method that works in all cases, right? So there is no one best solution. All of these are possible solutions, and the approach that you take is you allow for all these solutions in your toolbox. The user selects whichever is most appropriate for their application. So in this lecture, I'm not going to describe algorithms for extracting streamlines and so on. I think that's something that's beyond the scope of our class. But what I will do later, what you will do in your projects is you will use visualization tools that already implement these approaches. The paper that I have given for reading is your additional reading that describes these methods. So once you know what these different methods are, you essentially use them. Now, if you are interested further, you can look at papers that talk about the algorithms for computing streamlines. Right. So of course, streamlines can be combined with color. So for example, here, the streamlines on the right are shown, and there is a color associated also. The color is used to indicate the magnitude, or no, let me take that back, the direction of the vector flow, right? So one direction, the x direction, I think, is mapped to red, and the y direction is mapped to blue. So any combinations of them is what you see, blue to red. So often a combination of multiple representations are used to generate your final visualization. So this data is something that we will see a few times. So I'll explain a little bit. So here is a flow that seems to start from the left. Hope you can see this. The flow is streamlined, as in all the directions, the flow is moving towards the right, x direction. But as it goes forward, it hits an obstacle. Here it's a square obstacle, and it has to flow around this obstacle. Now, what happens when it flows around this is there are turbulent structures formed in the wake. So this is similar to the wake of a ship, right? So the wake here is turbulent, and that is what you see in the streamlines as well. Initially, the streamlines are all parallel to each other, and then in the wake of this obstacle, you have a lot of turbulent behavior. Right. So streamlines help understand this kind of overall behavior of your vector field. So just to summarize, the two techniques we saw were classical techniques. Glyphs like arrow plots, they are best suited for small data sets. Of course, if you try to place a glyph at every location, you will get a cluttered visualization. One way to improve the result is by thresholding and showing only those arrows that are above some magnitude. Streamlines do scale to slightly larger data sets. But again, if you show many streamlines, this will cause clutter. The quality of the visualization depends on how many streamlines you show and where do you show them. So where are the seed points, right? Again, depending on where you seed these streamlines, you may lose or gain important details in the field. So an important research question is, how do you find a good collection of streamlines? Streamlines and glyphs work in 3D as well. So I've just shown some pictures here. The picture on the left is just glyphs in 3D, but what you are seeing here is just a slice. Again, we use the same slicing technique to show a 3D vector field by looking at it one slice at a time. Of course, otherwise you have a lot of clutter. On the right, you see some streamlines, but here is an interesting user interface. What is done is the user is choose this kind of a so this is vector field from within the body. Looking at as I understand, this is some biostatistics study where you look at the ion distribution within the body. Now the line here is a way to choose your streamlines to seed the streamlines. And there is also individual points that you can choose, which correspond to local sinks or sources. And this helps because you, for example, you can equally sample this line and select seed points and see where they go. This is an often used interface. And now, of course, you can move this line wherever you want and interactively extract the streamlines to see how your vector field behaves in the neighborhood of this line. Right? So this is like taking a magnifying glass, except that the magnifying glass is not a circular glass, rather it's this line. And this line is used to query your vector field in the neighborhood of that line. A second class of visualization techniques, more modern techniques, are called dense visualization techniques. So here, what happens is you try to form an image rather than a collection of curves to create your vector field visualization. One technique that is used here is called line integral convolution. And you see an example here. It beautifully represents the behavior of the vector field, but this is essentially an image. It's a raster image. Here is another example in without color for the same flow, but now the flow is behind a circular obstacle. And you can easily see the turbulent structures being formed in the wake of this obstacle. What is a line integral convolution? Here is a one slide explanation. Again, I'm not going to talk about algorithms for computing line integral convolution images. It's good for you to know that these are different ways of visualizing vector fields, and you start using them. That is the idea. we will spend much time talking about algorithms for scalar field visualization, so that we can focus on one aspect and then go deep into that aspect. So what is a line integral convolution or a Lick image? You have your vector field as input, as shown here on the lower left. You take an input image, which is a noise image, random noise, right? And what you do is you use the vector field to convolve. At each point, what you do is you compute this line integral convolution, which is computed as follows. Given a parameter called L, so you use a curve centered at, so let's say you have a point here, which is shown here at the origin. You convolve along the streamline, passing through that particular point for a length 2L, right? And that convolution is what you get, what you compute for every point, and the resulting image is shown on the right. So those of you who have done image processing may have done convolution with with different kernels, right? So here what we want to do is really 1D convolution. So you are essentially computing this integral along the streamline. So what this does is it uses the noise image. Since it's convolved along streamlines, you capture the essence of the streamlines in your dense image. But of course, the output is no longer a collection of curves, rather it is an image. This is a big benefit, because with the image, you can do other kinds of processing and quick computation and so on. Right? So the Lick images are very popular in visualizing 2D vector fields. So here is a 2D vector field visualization using Lick. But the difference now here is that the vector field changes over time. So the Lick images have to be coherent when you compute it across time. So that is, you compute the Lick at every, then you blend all those time steps together to form a video. So in addition, what is done here is to enhance the vector field. What is done here is to use more opaque color for higher velocity regions, so that the higher velocity regions are highlighted. So as you can see, this is actually the Gulf of Mexico. There is a big stream and the velocity is high as it goes out, right? So this is called, this is again called Lick visualization, but for what is called unsteady flow or time varying flow. There are several other methods used for dense visualization. This is just a sample. I'll say one sentence about each. On the left, what you have is, let's go back. On the left, what you have is a visualization where you use a die source die at every source and sink points, and you let the die diffuse and display the color that you get due to this diffusion process. This indicates how the vector field affects, for example, color that is sampled within the domain. This is one way of understanding the vector field. Second is to, on the lower left is a visualization where you deform the Cartesian grid and subject it to deformation with respect to the vector field. This also gives you an indication of how the vector field behaves in different parts of the domain. On the right is Lick together with some kind of dye advection or a dye diffusion. So you put different colors at different sources and sinks, so to show you the effect of each source and sink. On the top right is a visualization where the vector field is shown like a comet. So this is quite common to visualization that is used for displaying wind, for example. What you see is the movement of the vector field over time, and the direction is indicated by the tail of the comet. So here color is again used to indicate different source and sinks. So that, as you can see, there are a plethora of techniques, and several visualization tools support at least a small subset, right? So the idea is for you to get a practical understanding of these techniques by working hands-on with data. This does take time, right? It's not something where you have a recipe from a book and you directly get an answer. You will have to spend time working with the data, understanding the visualization techniques one by one, and then choosing one that is most appropriate. So to end, vector field, the techniques that I talk about extend to 3D as well, but not as nicely as the scalar field visualization techniques, primarily because there is a lot of clutter when you go to 3D. For example, when you try to do lick and use some kind of volume representation to show the lick in 3D, all you see is a cluttered image and not very useful. So these techniques usually fail because of the size of the data. There is a lot of occlusion or clutter, and the field is itself very complex. So what you typically see in 3D is extensions of simpler techniques like streamlines, where you can say, I choose only a small collection of seeds and display the streamlines. Now the collection of streamlines will form a surface. So the definition is the same as streamlines, but instead of curves, you have surfaces now. Right. Again, I'm just showing you pictures without talking about the algorithm. This is a video that shows some streamlines, stream surfaces in 3D. So this is again the same simple example of a flow behind this obstacle. So here the obstacle is an ellipsoid. So this is a good academic example because of the turbulent structures being formed. What you see in color is just different time steps. That's all. This is just to indicate that you are sampling across time. The vector field changes over time and you see a lot of turbulent structures. And what is being displayed is the stream surface now, but there's a lot of transparency used so that you can see through. I'll move to an application of this. For example, stream surfaces are used to study the flow around vehicles for aerodynamic design. You can see that the car is well designed, so there is no turbulent structures formed except for a few near the boot of the car, and you see also some turbulence near the side mirrors. So these are aspects that are used in aerodynamic studies. So here is a zoomed in version which shows the turbulent structures. Okay. So finally, there are other techniques that are helpful in 3D. Similar to your stream surfaces, you can take a bunch of points and advect them. Advect them as in think of these points as dust particles that move over time and subject to your, let's say if wind is your vector field, subject to wind. So you get visualizations such as this. So here the structures are buildings and you see the wind is moving around the buildings using a technique called particle advection. So each particle is advected over time and you trace its path and display it as a curve. These collection of curves are displayed together using transparency. Right? So this gives you an overall idea about the vector field. So that was essentially a collection of various techniques for vector field visualization. There are more sophisticated techniques being developed now, which focus on the topology or connectivity. So here on the left, what you see is a vector field where blue indicates a type of critical point, for example, a sink, red indicates a source, and the yellow indicates saddle points. Instead of showing the entire vector field using the lick, one could show the arcs that you see on the right. This is called the vector field topology. So if you look at the region bounded by these white arcs, so let's take one example. So here is blue to yellow to red and back to yellow. You see that the flow in the interior of this region is more or less streamlined. There are no turbulent structures and so on. So the white curves seem to separate the flow into regions of good behavior. So these white curves are called separatrices. The field of vector field topology focuses on extracting these separatrices and using them to visualize vector fields. Right? So I will end there. So this was a quick survey of various vector field visualization techniques. The takeaway here is that there are many techniques, and there is no one technique that works always. But if you want to start understanding a vector field, maybe the best bet would be to start with something as simple as streamlines or arrow plots and glyphs, and then work your way up towards more sophisticated techniques. So this is what I hope you can do in your project as well. There is going to be a lot of guidelines given by way of references and papers. You want to start with that and use the visualization tools to generate different visualizations. You don't necessarily implement the details of each visualization technique. For example, you don't have to necessarily implement lick or streamlines, but you use them. Of course, you may have to do some scripting and implementation to decide which visualization you want to choose. Right, so that's the idea. And that's why I wanted to talk about this topic at an overview level. So I will end there. If there are any questions about this, I'm happy to answer them. And after the questions, like I mentioned, we can go over to Mohit, who is willing to answer your questions about the assignment. I will also be here, but I guess he will be able to answer the questions that you have. Yeah, any specific questions about vector field visualization? This is often called flow visualization in the literature. There is one paper that I have given to you as assigned reading. I ask all of you to read this. This only introduces the different techniques. It's nice in that way. It's introductory reading. In visualization. And even otherwise, it will give you a good idea about the topics that I covered in today's lecture. Okay, there's nothing specific, then maybe we can stop this here. Mohit is here. Okay, so let me stop the recording.